Here we have the infinite series 1 dividing by the square root of n times n plus 5. And we want to use the limit comparison test to show that this series diverges. And so once again, if we want to use the limit comparison test to show that a given series diverges, we have to show two things. First, we need to come up with the series b sub n, and then show that the limit of a sub n divided by b sub n is equal to a positive finite number. And then the second thing is we have to show that the series b sub n diverges. Then we can claim that the given series diverges. So first, let a sub n be the given sequence here, and then we just let b sub n be something similar. And here we can just let it be without the 5. And so next, we need to show that the limit of a sub n dividing by b sub n, we have to show that this is equal to a positive finite number. So this will equal to that. And recall that dividing by a fraction is the same thing as multiplying by the reciprocal. So that's why this expression right here ends up on the top. So this is equal to this. And the top here we just get n squared. Or we can just do it this way. So let's simplify this a little bit. So this is the square root of n squared, and then the bottom is the square root of n squared plus 5n. And then we can divide the top and the bottom by the square root of n squared. Since n is approaching positive infinity, so we don't have to worry about negative or anything here. So this is equal to 1. And then here we can combine them. So this is the same as this. N squared divided by n squared is 1. And then 5n dividing by n squared will be 5 over n. So one more time, n squared divided by n squared is 1. 5n divided by n squared is 5 over n. And then as n approaches infinity, we get 1. And then we get 1, and then 5 divided by n, that would be 0. So altogether we get 1. And so we have shown the first part right here, we've shown that the limit b sub n divided by b sub n is equal to a real finite number, positive. And so our objective is to show that the given series here diverges. And so we have to show one more thing before we can claim that this series diverges. We also have to show that the series b sub n diverges. And so the series b sub n is the without the phi. This series right here this will be n squared. N times n is n squared, and the square root of n squared is 1 over n. This n right here, this is n times n is n squared, and square root of n squared is just n. And this is a harmonic series. And it diverges. And again, the series 1 over n, we could also think of it as a p series, because 1 over n is the same as n to the first. This is also a p series with p equal to 1, and it diverges. We call it for a p series, a p is between 0 and 1 or equal to 1, and series diverges. So we have shown two things. We have shown that the limit a sub n divided by b sub n is equal to a positive real finite number, and then we have also shown that the series b sub n diverges, and therefore we can claim this series right here diverges by the limit comparison test.